Welcome back to Friedel-Crafts Alkylation. This is section 5 in the Klein's Organic Chemistry textbook. And this was discovered in 1877 by Friedel and Crafts, two people. And it's a very important reaction for creating carbon-carbon bonds. So if we have this guy here, and we treat this with I don't know what, let's choose a secondary alkyl halide and choose our catalyst, aluminum trichloride. And so here we'll form this guy here. Okay, so that's a new carbon-carbon bond, and that's very, very important. We've learned very few ways to create carbon-carbon bonds so far in this class, but that's at the core of chemistry, organic chemistry, building up more complex organic molecules, okay? So you want to put this on a special sheet of lists of those carbon-carbon bond-forming reactions, okay? Now, this chemical reaction proceeds through carbocations, so you might need to review carbocation stability, resonance, and rearrangements, okay? It's a pretty complex reaction, and this is the bigger section in your textbook that you want to pay attention to, okay? So let's go ahead and look at some the curved arrow reaction mechanism. Okay, I'll choose isopropyl chloride. It's just easier to draw that, I guess. So let's take benzene here, and let's treat it with 2-chloropropane, aluminum trichloride, and that forms isopropyl benzene. Now, aluminum trichloride is the catalyst, so you might use 1 mole of benzene, 1 mole of 2-chloropropane, and maybe just 10% of that, which is 0.1 moles of aluminum chloride. Aluminum chloride is regenerated in this chemical reaction. We put catalyst below the arrow usually, okay? So as I mentioned before, the first step usually is to create the electrophile. And so here we want to use the aluminum trichloride as a Lewis acid, okay? We can take the lone pairs on this chlorine atom of our organic alkyl chloride, okay? And we're going to go ahead and just attack the aluminum to form our Lewis acid base complex. Now, in this particular example that I'm showing you here, we have a secondary alkyl halide, and so for this textbook, it's okay to form a secondary carbocation. So what we want to do here is well, let's draw our charges. This whole thing right here is the leaving group. So this is very similar to the electrophilic aromatic chlorination reaction. And so here we're just going to depart that guy there, okay? So this first step is attack. We're taking the chlorine of the alkyl chloride and attacking something. And here we're eliminating that whole leaving group, okay? Elimination. So here we form the carbocation, which is secondary, okay? And that is the electrophile, okay? And you should have familiarity with nucleophiles wanting to attack carbocations, okay? So that's the key business end. Let me just show you what happens to the rest of this. We form, let's see, I'll squeeze it in over here. We form this guy here, okay? And chlorine can leave, okay? And this can be in equilibrium with aluminum trichloride and chloride ion. And I just wanted to point out that aluminum trichloride is catalytic. It, you know, for every single conversion, it's recreated so that it can go on and catalyze more events, okay? So the electrophile then gets involved in the next part of the reaction. Let me show you what happens. So here we have benzene, and once again I'll highlight the hydrogen that we want to substitute for an isopropyl group. and I have a secondary carbocation. And so I'll use curved arrows here to show how the pi bonding electrons attack that carbon. Okay, so A for attack here, and we form the usual sigma bond complex, the book calls it. Okay, it's a nice resonance stabilized guy, but it's not aromatic. Okay, there's not a p orbital on every atom of the ring. Okay, so it's not aromatic anymore. It's just a super conjugate. It's a conjugated resonance stabilized carbocation. But way better than that is an aromatic ring. As I mentioned in the previous page, we can have chloride floating around from the aluminum chloride and the leaving group, and so chloride then can come in and deprotonate this proton right here. Okay, technically the beta hydrogen, kind of like a E1 reaction, and so this elimination step will give you isopropyl benzene. Sorry, that's not an elimination, that's a deprotonation step. So this will give you isopropyl benzene. Okay. All right, so let's review a little bit about carbocations. So if you have an aromatic ring and you treat this with that example I showed you in the beginning, okay, we would expect to get the product here, and that's going to proceed through a secondary carbocation. Okay, and secondary carbocations are allowed. You can draw those, they might form. Same with tertiary carbocations. So if we have something like this and we form we add tert-butyl chloride, aluminum trichloride catalyst, we would form a tert-butyl benzene, and that also is very nice reaction, and that proceeds by way of a tertiary carbocation. And we know that tertiary carbocations are the best. Okay, now keep in mind that you can make carbocations in different ways. So for example, if you took benzene and you treated this with cyclohexanol and sulfuric acid, say for example, you could make cyclohexyl benzene. And you might be wondering, what? There's no aluminum chloride in there. But just think carefully about how that might occur. If you have cyclohexanol, okay, and sulfuric acid, remember, is a source of protons, or H+, and so if you protonate the hydroxyl group here, water, once again, is a good leaving group. Okay, and you can kick off water and get the secondary carbocation, which, you know, reacts with benzene and does its thing to give you the product. Okay, so secondary carbocations, great, good to go. Tertiary carbocations, great, good to go. Now let me show you some limitations of the Friedel-Crafts alkylation. Now, if you take benzene and you react this with 1-chloropropane and aluminum trichloride, what you get is a large amount of the isopropyl benzene and minor amounts of the propyl benzene. Okay, so this is the major product and this is the minor product. Okay, so there are 2 points to talk about. This one here on the right is produced by an SN2 reaction, and that's because you cannot form a primary carbocations. okay? The one on the left does form from a secondary carbocation, but that has rearranged, okay? Rearranged. And that's fairly obvious. We're starting with a straight chain alkyl halide, and we're getting a branched alkane attached to the benzene. So I want to show you these kind of mechanisms here, okay? Now keep in mind that primary substituents and even methyl substituents work just fine. So if you treat this with chloroethane, for example, and aluminum chloride, you do form ethyl benzene here in great yield, and that also forms by SN2. Okay, you're not going to form a primary carbocation. So let me show you the mechanism for the minor product and then show you how this guy rearranges, okay? So once again, in this reaction, you want to take the chloropropane that you're hoping to react this guy with, and the first step has to be this. Aluminum chloride comes in, complexes with the lone pairs on the chlorine to give you an acid-base complex, a Lewis acid, Lewis base complex, okay? So we put the charges here and lone pairs everywhere if you want. Okay, so this is our complex. Now the complex can react with benzene directly in an SN2 reaction. So here's benzene. I'll draw in the hydrogen just to keep an eye on that. And I want to redraw this over here. I'll leave the lone pairs off so it's easier to take notes on your end. And so what we want to do now is take the pi bonding electrons as usual, and what we're going to do is an SN2 reaction. So we're going to attack this primary carbon and kick off the leaving group, okay? So that's an SN2 reaction. And so what we would get here is the sigma complex, or the intermediate, okay? So let's draw that in. Draw our hydrogen, and then in purple, I know there's a lot of colors here, but this is where I want to add the straight chain with the 3 carbons. So that's my purple group that's been installed, okay? So that's the carbon-carbon bond forming step. And then at the end, you know, we have chloride deprotonating, okay? So chloride's floating around, and we want to deprotonate that guy there. And this gives us, once again, the minor product, okay? Minor product. Now, this is the minor product. So, okay, it's an SN2 reaction, great. We can do that to make toluene with a methyl group. We can do that with an ethyl group to make ethyl benzene, and so on like that, okay? Now, with the propyl group, there's a chance for a rearrangement, and you get isopropyl benzene as the major product. Now, how does that occur, okay? So first of all, the first step still remains the same. You have 1 chloropropane. That reacts with aluminum chloride, and that still gives you this complex, okay? I'll leave the lone pairs off so it's easier for you to take notes there at your house. So we have this intermediate, okay? And that's our electrophile. Now here, what we want to do, before benzene even comes in and approaches close enough to this molecule to attack it, we want to do a rearrangement. So let's label these carefully. This carbon right here is a primary carbon. We cannot form a primary carbocation, but we can form a secondary carbocation. And whoops, I wanted to say carbon, not carbocation yet. Okay, so what we want to do now is take this hydrogen with the lone pairs and do a 1,2 hydride shift. Okay, 1,2 hydride shift. So we saw this when we were talking about rearrangements of carbocations. So this is a 1,2 hydride shift, And what we're going to form is a secondary carbocation. Okay. And it's okay in stability. I'm not saying it's the best, but it's way better than a primary carbocation. And this apparently happens so much so because the benzene at this point, and this is just one possible mechanism for this, but now at this point, we're going to do the rest of the mechanism. So, you know, we have our benzene now that, oh, here's a secondary carbocation. And so it's going to attack that. So we'll use, I guess, yellow arrows here for the curved arrow reaction mechanism. So the pi bonds of this benzene now will attack. We will form our resonance stabilized guy here, and here's where you have the isopropyl. Okay, so in the previous mechanism you had the propyl because it was SN2, it didn't have a chance to rearrange. Here it rearranged, so you're forming isopropyl as the bonding carbon to this guy. And the last step, once again, is chloride coming in and deprotonating that. Okay, so that's going to give you the major product. All right, so let's go ahead and look at the reaction again as an overview. So it's a limitation in that if you take an alkyl halide that's primary, you're going to expect the major product being the rearranged, okay? And you would expect minor products, okay? If you have a primary alkyl halide that cannot rearrange, there's only one possibility, and you form the major product, okay? So that is a tremendous limitation of the Friedel-Crafts alkylation reaction, and that's something to really make sure that you write down in your notes. Some other examples here are as follows. Okay, these are from the book here. So if you take this guy here and you treat this with chlorobutane, 1-chlorobutane and aluminum chloride, what you need to recognize is that the halogen is connected to a primary carbon, and adjacent to that is a secondary carbon. So when we draw the products here, we can draw the carbon of the benzene ring here connected to the primary carbon to give you a straight chain alkane, or you can draw the benzene ring here. This carbon, we'll just pick on that one, attached to the secondary carbon. And if you do that, that's a major product because that's the rearranged. Okay, so this would be expected to be the major product. This would expected to be the minor product. Okay, in the book, I'm not sure what the literature reference is. They state that this one is a 35% yield and this is a 65% yield. So don't worry about the numbers. We're just concerned about labeling things as major or minor, but I just wanted to cite this with some evidence, okay? Now keep in mind that there are a couple other limitations. Okay? You can't make aryl carbocations. So, for example, benzene with a plus charge here is not good. So if you take benzene here and you try to treat this with chlorobenzene and aluminum chloride, there's no reaction here because this carbocation is extremely unstable. It's not sp. It has a hybridization conflict, basically. Okay? You also can't form vinyl carbocations. This is a vinyl carbo. Let me just draw it like this. I'll draw an H and then I'll draw a plus charge there. So these are notoriously high in energy, and what's observed is they don't form. So for example, if we have benzene and we want to try to treat this with, you know, the correct catalyst, and you try to add this guy here, there's no reaction. So that's what's observed, and we explain this in hindsight by saying these kind of carbocations don't form, they never form, they don't work in Friedel-Crafts reactions, okay? So that's the secondary, that's the second limitation I wanted to talk about, okay? The other thing that happens is that sometimes you get overreaction. Okay, so this is another limitation. Okay, so let's say, for example, you have a benzene, which is reactive, and we treat this with, let's do chloroethane and aluminum trichloride, and you make ethyl benzene. It turns out that ethyl benzene is slightly more reactive. So guess what? As soon as the first few molecules of ethyl benzene are created in your reaction mixture, they're going to be more reactive than the benzene molecules that are present in solution. So they're going to react a little bit faster towards more chloroethane. Okay, and I'll just draw the para product here. Don't worry too much about things like this right now. We'll talk about selectivity and directivity and stuff later on. But so basically what happens is, if you take benzene and you try to treat this with chloroethane and aluminum chloride, you can get the expected product, you know, and hopefully that's major, but oftentimes you have significant amounts of over-alkylated products. I think that might be covered by my picture, so I'll write it on top. This is the over-alkylated product, okay? This isn't something we need to really worry about on paper. In lab, yes, you would have to worry about that, okay? The third limitation, and this is very important to know about this, is that this reaction does not work with the nitro group, okay? Okay, so we saw, for example, if you take benzene and you were to treat this with a chloroalkane, aluminum chloride, you indeed would get an alkylated product. Okay, no problem. If you treat this with, you know, something that has maybe, like, say, a chlorine group on here, that'll work just fine too. Okay, I know there's lots of chlorines here, but the one you have to worry about is this one. This one becomes activated by the catalyst, and you do indeed get the methyl group being introduced onto one of the carbons of the aromatic ring. I'll just draw the ortho product here. Don't worry too much if that's correct or wrong at this stage, okay? So that works just fine. Now, a reaction that will not work is one in which you have a nitro group. So if you have a nitro group on your aromatic ring, we'll learn in subsequent sections that the nitro group is such a potent deactivator, it really makes the aromatic ring very unreactive towards electrophilic aromatic acylation and alkylation. So here we go, aluminum trichloride, no reaction. Okay, so watch out for the nitro group. There's no reaction with nitros. Okay, I know they're kind of cool sounding and stuff, but yeah, watch out for that. There will be no reaction. Okay, the nitro group and other very strong electron withdrawing groups. Right now, EWG might be a foreign topic for you, but that's fine, okay? So that's pretty good. That's pretty cool. You might want to think about some synthesis problems. I don't see any kind of thing here on the book. Wait a minute. there's they discuss side chain manipulations at this point, so I do want to mention that. Okay, now let's talk about further synthesis. Okay, so let's talk about aniline. Okay, aniline is an aromatic ring with an NH2 group attached to it. Okay, and that's used in the manufacture of different dyes, for example. Now, how is that made? We of course start with benzene. We treat this with nitric acid and sulfuric acid. Okay, I'm not sure why they're putting this at the end of this chapter on Friedel-Crafts, but I just wanted to put this in there so I don't skip it. We form the nitro benzene. Okay, so that's nitro benzene. We've talked about that, and that's great. Now, the new thing I want to talk about here is that you can actually perform a reduction of the nitro group, and there's like many different ways of doing this. The one that Klein uses is zinc and hydrochloric acid. Okay. In your textbook, if you have a different textbook, it might be tin and HCl. Tin is SN. It might be iron and HCl. Okay. In this textbook, they choose zinc and HCl. Okay, so that's pretty cool. So yeah, we will stop here at this chapter. Thanks for watching. The Friedel-Crafts alkylation is a pretty big part of the chapter, so look at the practice problems later on. Okay, thanks for watching.